Well, good morning. Oops. Glad to see everybody here all bright-eyed and bushy-tailed. So, before we get started on any questions from the homework, I want to reiterate something. The semester is more than half gone. We are on week 9. Now, I have all semester I've been more than happy to accept your assignments and your homework late, and I still am. I want you to earn the points, so I'm not penalizing anyone for any late homework. But I cannot wait until the last week and get a big pile of papers to have to grade. I have a deadline by which I have to turn in all of your grades, and I don't get any grace period. So the day is coming, and it's coming soon, that I'm going to call an end to turning in late homework. And at that point, anything that you have not turned in, that you've not gotten a grade for, will turn to a 0. And when that happens, it's going to hurt your grades. So, for the next couple weeks, I want you to make it your business to go get on Canvas, find out what you're missing from the homework assignments, go back, do them, get them done. I want to give you the credit. I want to give you the points, but I need you to do the work. So get them done, get them turned in, so that I can get them graded, because it's not going to be too many more weeks before I'm going to have to say, okay, that's it. This far and no further. From now on, anything that's not turned in on time just won't be turned in. So, also, if you have missed an exam, that is another one that you need to get with me so we can see about getting you a makeup exam done. All right? Honestly, as a class, it doesn't look like y'all are going to need it. But if there's time at the end of the semester, I would also like to do a bonus exam that y'all could take and maybe use it to replace one of your low grades. But that, of course, will depend on whether or not there's time to do so. And like I said, honestly, as a class, y'all are actually in pretty good shape. Hopefully it'll stay that way. Has anyone not signed in? All right, here you go. And make sure they get it too. Next week, this is week 9, so today and Thursday is week number 9, and the following week will be week number 10 out of, 15? Of course, there's a spring break week in there somewhere. Oh, you already know, huh? You're looking forward. I have no idea when it is. But you got
to make sure you don't sign anything that weekend, because they won't do it. The next week, we have another exam. It will be on chapter 3.1 through 3.4, which we are going to cover today. And so today we're going to cover, after we do questions from the homework, we're going to cover chapter 3.4. And then Thursday, be here, bring your homework, and be ready to ask questions, because Thursday we're going to review everything we've covered in chapter 3 to prepare for the exam next Tuesday, a week from today. All right? So, now, if you make the choice, because you're all grown-up adults and you get to make your own decisions and you don't need my permission to decide whatever you choose to decide. But if you choose to decide that, well, since Thursday's just a review, you're not going to bother to show up, good luck on the exam. Okay? But don't miss the review and then come crying about you didn't know what was going to be on the exam. So, if it sounds like I'm getting a little hard-nosed, I want you to understand why. Because the end of the semester is coming up, and you're all in very good shape. I really don't want to see anybody mess up that. I said power off. Nobody else has interrupted my class with cell phones. None of my friends are either. No, I really do. I want you to do well. I want you to know. I want you to understand the gravity of the moment. It's that time. It's that time when people if you need to make up some grades, if you need to get your grade built up, now's the time to do it. You know, in the last week and a half, it's too late. So, now, we already heard the first question, and problem number 69 seems to be given 77. 69. That's why I was asking what you said, because that one is just.
No, I was just looking at the 69.
Okay, so you want to do what? You want to look at 77, 3 times 1 minus cosine theta equals sine squared theta. All right, well, let's see if we can figure our way through this. 3 times 1 minus cosine theta is equal to something. Make sure I even wrote that part right. Is equal to sine squared theta. All right. Well, we could start by multiplying this out. 3 minus 3 cosine theta equals sine squared theta. All right. Yeah, you know what? I'm not sure that's a good way to go either. I think this is one where we end up having to use some fairly obscure identities. Everybody just hold on for a minute. I'm going to just wait right there for a minute, and I'm going to go get my folder for this class. I need to do that anyway because I've got some homework to hand back to y'all. And I forgot the folder in my office, but I've already worked out these problems, and I don't want to go chasing down a rabbit trail and just confuse everybody. Wait right there 1 minute.
What number was it?
77. Tyler, you got yours done.
What?
You got your homework done for here?
No, not my one. I'm trying to look back there.
Where's the sign-in sheet? Is anybody not signed in? Thank you. All right. Oh, all right. There you go. Ah, yeah. I remember this one now. This is one that I started working it too, and it was like I'd worked, I went through like a half a page of algebra and realized I was running right up into a brick wall dead end. So this one is kind of obscure a little bit.
There we go. All right. In this one, we're going to make use, as in most of them. Where did my marker go? As in most of them, we're going to make use of the identity sine squared theta plus cosine squared theta is equal to 1. Is everybody familiar with this identity? Everybody already knows this because this is pretty much for all of these homework problems. That's where you need to end up at. Now, because sine squared theta is equal to cosine squared theta, so sine squared theta plus cosine squared theta equals 1, we can also write sine squared theta is equal to 1 minus cosine squared theta. Right? But what is 1 minus cosine squared theta if we factor it? We get sine squared theta is equal to, this is the difference of squares. 1 is 1 squared minus cosine squared theta. And when you factor the difference of squares, it's 1 minus cosine theta times 1 plus cosine theta. Right? Does everybody see how we get there? If you multiply these two together, 1 times 1 is 1. First, inner is minus cosine theta. Outer is plus cosine theta. Last is minus cosine squared theta. These cancel and you end up with 1 minus cosine squared theta. So this is just this factored. And this is equal to sine squared theta. So let's rewrite this equation. 3 times 1 minus cosine theta is equal to 1 minus cosine theta times 1 plus cosine theta. Now how's that for an obscure backdoor to come through? Huh? Yeah, well, at that point, you divide both sides by this, and you end up with 3 equals 1 plus cosine theta. Right? Subtract 1 from both sides, and what do you get? 2 is equal to cosine theta. Right? How is that possible? What is the range of the cosine function? Think back. Domain and range. The domain of sine and cosine both is minus infinity to plus infinity exclusive. What's the range of cosine theta? Negative 1 to 1. Thank you. So what angle theta could possibly give you 2? None. There is no angle theta for which the cosine of that angle is 2. Therefore, the answer to number 77 is there is no answer to number 77. No solution. They have what?
They have 0. They say no solution for A1, but for 77 they say 0.
How is that possible?
I didn't even look yesterday.
No, I'm sorry. There's no. The answer to this, 2 can never equal 0. Well, if this is, well, hold on a minute. We've got sine squared theta here. Well, what's sine of 0? Sine of 0 is 0. What's cosine of 0? Is 0. So, no, cosine of 0 is 1.
Okay.
So 1 minus 1 makes this a 0. That would be a 0. 3 times 0 would be 0. Yep. 0 will work. How did we get a solution? Ah. Okay. Nope. This is pretty plain. If anyone's paying attention, you can see where the solution went wrong. There is, in fact, no other solution besides 0. But what happened? I skipped an important point, an important step in working this solution. What is it? No, sine squared theta is simply 1 minus cosine squared theta, which is equal to 1 minus cosine times 1 plus cosine. And that's what I did here. I replaced sine squared theta with this. But then what did I do? Come on, think back. I showed you the proof that 2 is equal to 1, right? Huh? No, it works. What happened right here? I divided both sides by 1 minus cosine theta. Well, that is only valid if cosine theta is not equal to 1. Because as soon as cosine theta is equal to 1, this is 0 and that's 0. And you can't divide by 0. So what this shows is that for all other angles, there is no solution. But because of this right here, as soon as I had to divide through by 1 minus cosine theta, I should have checked to make sure that 1 minus cosine theta is not equal to 0. I should have stipulated when 1 minus cosine theta is not equal to 0. You can divide it out. When is it equal to 0? 1 minus cosine theta is 0 when theta is 0. So there, right there, is our solution set. When 1 minus cosine theta is equal to 0, theta is equal to 0. And that gives us our solution set. Everybody see that? Oh, look. I even caught it on the answer key. I did catch it when I was working the answer key. Does everyone see how this worked? How this happened? How this worked? No.
1 minus 1.
Right, and cosine theta, cosine of 0 is 1. So when theta is 0, 1 minus cosine theta is also 0. And this, you can't, and that makes this step invalid. So at this point right here, as soon as I divided through by 1 minus cosine theta, I needed to make certain that 1 minus cosine theta was not equal to 0. Any more questions on this one? Or on any of the other homework problems? Okay, let me rephrase the question. Is there anything any of you think that the person sitting next to you wants to know about, or any of the homework problems? Anything in the homework that you just want to look at because, you just want to see it? Say again? 30? Tangent of 2 theta equals minus 1? Is that the one? All right. Everybody got pictures of this one before I erase it? All right. So, we're looking to solve the equation tangent of 2 theta equals minus 1. So, what's the inverse tangent of minus 1? Say again? No, the inverse tangent of minus 1. What angle of theta will give you a tangent of minus 1? Look at our unit circle. For the tangent to be 1, it has to be, plus or minus. It's got to be one of the pi over 4s, where sine and cosine are equal. Because tangent is sine over cosine. Okay. Well, it's not minus here. Because here you've got minus sine divided by minus cosine, so this is a tangent is positive. This tangent is negative. This tangent is positive. And this tangent is negative. So, now we're told to solve this equation. Let me make sure. Yeah, we are working on the interval of 0 to 2 pi. What is the domain of inverse tangent? Now, what the domain of the inverse tangent function is restricted to minus pi over 2 to pi over 2. Those two principal asymptotes. So when you take the inverse tangent of negative 1, you're going to get 7 pi over 4. But we're looking for the whole interval of 0 to 2 pi. So again, you can use the calculator to do the arithmetic. You have to do the math. We're also looking for 3 pi over 4. Okay? But there's another rub here. What is the period of this function here, tangent of 2 theta? The period of tangent of 2 theta, omega, is 2. So the period of tangent of 2 theta is, what's the period of, no, 2 pi is the period of sine and cosine. Pi is the period of, so this becomes, what? Yeah. So the total period of this is pi over 2. So we're going to go through 2 periods of pi over 2 to go from, we're going to go through 2 full periods of this in order to go through one rotation of 0 to 2 pi. You understand? Because we're going through to 2 theta, we start here. If this were a sine or a cosine function, we would go through the whole period, one whole period of sine going from here to here. And then we would go through a second period of sine going from here to here. Because this is a tangent function, the whole period normally would just be from here to here, so we're going to go through a whole period just getting to here. And then we're going to get to another whole period getting to here, and then another whole period getting to here, and another whole period getting to here. All right? So, to these solutions, 7 pi over 4, we add another period. And to this solution of 3 pi over 4, we add another period. Remember how that works? Everybody, 1 second here. I just missed an important step that I almost neglected. We got to here, we got 2 theta is equal to these solutions. We're looking for theta. So that would be 7 pi over 8 and 3 pi over 8. Right? Because we've got to divide both sides by that 2. Now, to those solutions, we have to add the extra periods of pi over 2. So we also have 7 pi over 8. Right. For theta equals 2 pi. But this function is going to 2 times theta, so we're going to 4 pi. to find the full solution set of this equation in that domain of 0 to 2 pi. That's basically we're adding 4 pi over 8. So that would be 11 pi over 8, and that would become, that would be 7 pi over 8. Which was already one of the solutions, wasn't it? Yeah, MS. All right. Me trying to do arithmetic again. Now I'm having trouble reading my own handwriting. Say again? Over 2, which is 4 pi over 8. Yeah, there's a whole nother cycle we got to add. Hold on a minute. Let me look back at something here real quick. No. Yeah. Yeah, we add the period of pi over 2. We end up with,
Where tangent equals -1.
say again?
The very beginning, where tangent is negative.
Right, that would be, it would be negative, tangent of 2 theta is -1 at 7 pi over 4 and at 3 pi over 4. Which means theta would be 7 pi over 8 and 3 pi over 8.
Right, I agree with that.
Right.
But that's where it's at. But the other solutions are not where tangent is negative.
No, it's when you add a period of this function. which is pi over 2.
Right.
That gets you to 11 pi over 8, which would be,
So it would be in the third quadrant.
yeah, well,
Because it's more than 8.
that would be 10 pi over 8, so it would be here. That's 11 pi over 8. But we're actually measuring double that, 2 theta. So 2 times 11 pi over 8 would be 11 pi over 4. So that would be 8 pi over 4, 9 pi, 10 pi, 11 pi over 4, which would put you right back here at 3 pi over 4. This should be 15 pi over 4. No. No, I'm trying to translate my own handwriting. No. Okay. Here it is pi.
If you just replace theta in that original equation with 7 pi over 8 and 3 pi over 8, it'll work.
Oh yeah, no, these are right. These solutions are correct.
Right, and our range is only 2 pi. But have to equal -1.
Right. But we're going, our domain is 0 to 2 pi for theta. But that means our total domain for 2 times theta is 0 to 2 pi times 2, or 4 pi. So we're basically going twice around. Oh, of course. We're not adding, yeah, we're adding no. Well, this is just really starting to twist my neck. Why did I add 11 pi over 8 to this one?
Oh, that's, here, we're adding a second period, okay? So we start at 3 pi over 8, and we add 3 pi over 8, we add pi over 2. That gives us, so we're adding 4 pi over 8, and that gives us 7 pi over 8. All right? But that only puts us to here. That adding that extra, I was adding to the wrong result. You want to continue from where you were. So our set, we want 2 more solutions because we got to go a whole nother round. So we add the pi over 2 to 7 pi over 8. Plus 4 pi over 8, and that gives us 11 pi over 8. That's our next solution. And that's what we add the next pi over 2. No. That brings us to 15 pi over 8. Now, multiply each of these by 2. You get 3 pi over 4, which is here. Multiply that, you get 7 pi over 4, which is here. Multiply this by 2, you get 11 pi over 4. It'll be 8, 9, 10, 11. Then multiply that by 2, and you get 15 pi over 4. 12, 13, 14, 15. That's what I was doing. I was adding, you don't add the period to the first 2 solutions. In point of fact, in this case, the second solution was adding the first period to the, adding pi to the first solution. To get the rest of your solutions when you're going through, you add the period to successive, you add this period of the function to successive solutions until you make it all the way to the end of the total domain, which in this case would be 2 times 2 pi or 4 pi. Have I thoroughly confused all of you? Okay.
I follow your math now, but I still think you're going 1 period too far because the statement limits the 2 pi.
Okay. Is 15 pi over 8 more than 2 pi? No.
Yes, it is because it's 15.
16 pi over 8 is how much?
Oh, I see what you're saying. Okay, all right.
16 pi over 8 is,
Now I'm following because that's actually,
that's 1 less than 2 pi.
right.
And remember, we're working with double theta.
Right, it only goes.
So, okay, everybody, let's start over so I can do this without confusing you or me. We're working with the function that we're working on to solve is tangent of 2 theta equaling -1. Take the inverse tangent of both sides, and we end up with 2 theta. It has to be equal to 3 pi over 4. But we want every solution for the full 2 pi, not just for the first solution. So we take theta now is equal to, because we're doing double theta, not just theta, 2 theta is equal to 3 pi over 4. That means theta must be equal to 3 pi over 8. All right? All the rest of this about periods and stuff,
We don't even need to concern yourselves with it at this point, unless you just want to understand what's going on. That's theta is equal to 3 pi over 8. Well, the period of this function, 2 theta, is pi over 2. So we have to keep adding periods. We know that at every period, it's going to equal -1 again. So if we're talking about the regular tangent function, then we get -1 at, actually in the real function, we get -1 at 7 pi over 4, or minus pi over 4. Okay? And if that's where you want to start, it'll still work. We could start at minus pi over 4. Matter of fact, let's do that just to maybe clarify some of this for you. Minus pi over 4. And that is within the domain of the inverse tangent function. All right? But it's not within the domain that we're looking for. Because we want to go from 0 to 2 pi. So minus pi over 4 would have to be rewritten as 7 pi over 4. How's that for thoroughly confusing? So let's go back to theta. 2 theta equals 3 pi over 4. We divide by 2, and we end up with 3 pi over 8. We know the period of this 2 theta function is pi over 2. So we just keep adding periods. We know that for every period, we're going to come back to this same value of tangent. So we just keep adding periods until we get to 2 pi. So we're adding the first period to 3 pi over 8. We add pi over 2, which means we're adding 4 pi over 8. So 3 plus 4 becomes 7 pi over 8. We're still not to 2 pi. We add another period of 4 pi over 8. That brings us to 11 pi over 8. We're still not to 2 pi. So we add another period of 4 pi over 8. That brings us to 15 pi over 8. And now if we add another period, we're over 2 pi. So this becomes our solution set. Does everybody see how that worked? It's also 0. Yeah. Any more questions from the homework? 35? Well, the whole point of this section of the book, this chapter, is to learn how to manipulate these things algebraically, mathematically. All right, 35. Tangent of pi over 2 plus pi over 3. Theta over 2 plus pi over 3. And that is equal to 1 plus 1?
Yep.
All right. Well, what's the inverse tangent of 1? So the inverse tangent of 1 is pi over 4. The inverse tangent of theta over 2 of that, the tangent of theta over 2 plus pi over 3 is theta over 2 plus pi over 3. And we can subtract pi over 3 from both sides. We end up with theta over 2 is equal to pi over 4 minus pi over 3, which is 3 pi over 12 minus 4 pi over 12. Don't let me do arithmetic in my head. After that last fiasco, I'm just double checking before I write anything down. Hey. Say again? Yeah, we'll get there. But there's a second solution here. Remember, tangent of theta is 1 at pi over 4. It's also 1 at 5 pi over 4. Right? So theta over 2 would be 5 pi over 4 minus pi over 3, which would be plus pi over 12. All right? Now, there's something else going on here I want everybody to pay attention to. What is the omega? What's the period of this function? Omega is 1/2. Right? So the period is pi divided by omega. But pi divided by 1/2 is actually 2 pi. So the period of this function is now all the way through 2 pi. So anyway, we end up with these two solutions of minus pi theta over 2 equals minus pi over 12 and pi over 12. And when we multiply both sides by 2, we end up with theta equals minus pi over 6 and pi over 6. Of those two, which are in the domain of 0 to 2 pi? Minus pi over 6 is not. So the solution set is just pi over 6.
That second one, pi over 5 minus 3, should actually be 11 pi over 12. So that's 15 minus 4.
5 pi over, that would be, okay, wait.
It'd be 15 minus 4, which would be 11 pi.
Right, you're right. 11 pi over 12. Okay. Now, I pointed out to you that minus pi over 6 is not in the domain of 0 to 2 pi. But there's something else interesting happening here. Because we are at 11 pi over 6, which would be 1 pi minus pi over 6 and 11 pi over 6 are actually the same solution. But because we've doubled the period of the tangent function from pi to 2 pi, now you're only going to get one solution per 2 pi period. Because unlike the that's one of the ways tangent is different from sine and cosine. You can get multiple solutions for sine and cosine. You'll get 2 solutions in every period. You only get one solution in every period of tangent. And in this case, that one is pi over 6. Did that answer the question? I forgot who answered it. Who asked for this one? That was you. Did that help? Yeah. Okay. Do we have any more? Well, then let's move on. Who can tell me who can answer this? What is an identity? Anybody? We've talked about identities. In fact, we used one just a minute ago. We have the identity sine squared theta plus cosine squared theta equals 1. Why is that an identity? What makes it an identity? It's always true for every value of theta. In general, a function f of x is an identity with g of x if and only if the equation is true for every value of x for which they're both defined. Okay, the example they use in the book is f of x equals x plus 1 squared, g of x equals, what's the square of that? X squared plus 2x plus 1? Yeah. G of x equals x squared plus 2x plus 1. That means f of x and g equals g of x is an identity because for every value of x, it will always be true. For every value of x for which they're both defined. What is an identity? What is it distinct from? What other kind of equation would there be? What is that? This is what we would call a conditional equation. In other words, it is it may be true for the right value of x. And in fact, that's what you use it for. You solve for x. X squared equals 2 and x equals square root of 2. Or 2 divided by the square root of 2, if you're in engineering. That would be a conditional equation. This would be an identity. Sine squared theta plus cosine squared theta is an identity. Equals 1 is an identity because it will always equal 1 for every theta. Now, how do we know that? You may recall last time I mentioned that I hadn't looked ahead yet, and I didn't know yet if we were going to cover identities in this course, but that if we didn't, I was probably going to add it next time. I don't have to add it next time. We're doing it now. Let's look at this one as an example. Let's go back to our unit circle. We have a point P of x, y, at whatever those coordinates are. X and y. And we know from our trigonometric definitions for that theta, the sine of theta, because r equals 1, the sine of theta is equal to the y-coordinate, and cosine of theta is equal to the x-coordinate. That's our definition. If you want to back up further, we could go to any arbitrary point where radius was equal to some value r, and now we know that r sine theta is y and r cosine theta is x, and we can divide through by r to get our definitions of sine and cosine. But we're working on the unit circle, so our radius is equal to 1. And we know that our radius, we can find that radius by using the Pythagorean theorem of a right triangle. And know that this squared plus y squared will equal 1. It'll equal that radius squared. Well, we know x and y are both the sine and cosine of that angle, so x squared equals cosine squared theta. Y squared is equal to sine squared theta. And that's equal to 1 squared, which is 1. And there we have our identity. In fact, it's called a Pythagorean identity. There's it's not the only Pythagorean identity. There are some others. Let's look at one of them. Tangent squared theta plus 1 equals secant squared theta. How can we prove that that is, in fact, a Pythagorean identity? And this is the point of this section, chapter 3.4. You're going to be working on demonstrating. That's the whole homework set is you're given equations, identities, and told to prove that they're true, or given equations and told to prove that the equations are true. And so remember this one. This one is your friend. By and large, when you're looking to prove an identity, if you can reduce it to the Pythagorean identity or to any established identity, then you've demonstrated the identity. Well, let's look at this one. A good first step for doing this kind of thing, for establishing these identities, is first rewrite the equation in terms of sine and cosine only. Well, tangent squared theta is simply sine squared theta divided by cosine squared theta plus 1, and that's equal to secant squared theta is 1 over cosine squared theta. Right? Okay, well, multiply both sides by cosine squared theta. These cancel, and you're left with sine squared theta plus cosine squared theta equals 1, which is your established Pythagorean identity. And so this way we have proven that tangent squared theta plus 1 equals secant squared theta is one of the Pythagorean identities. Not that it's any great mystery at this point, but how would we establish that as a Pythagorean identity? Rewrite it in terms of sine and cosine. Now we've got cosine squared theta over sine squared theta plus 1 equals 1 over sine squared theta multiplied through by sine squared theta, and you're left with cosine squared theta plus sine squared theta equals 1, and you've proven that this is also a Pythagorean identity. And in fact, either memorize this one or make sure you write it on your index card, because that's the mama you're going to always run home to when you start working on proving identities. All right. In fact, it is so common that you're going to find all sorts of variations of it. Cosine squared theta equals 1 minus sine squared theta. I think everyone can pretty well just look and see how you get that variation. Those of you in engineering and electronics, you're familiar with Ohm's law, and you're so familiar with it, you know I equals E over R, but you also know that R equals E over I, and E equals IR, because you manipulate it every which way. Same thing is true with this Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. It's going to get manipulated, changed in various permutations, but you will keep coming home to it. There are other identities that are definitions. We've got the identity tangent of theta equals sine theta divided by cosine theta. That's an identity because it is always true, but it's basically by definition. Same with cotangent. 1 over tangent theta equals cosine theta over sine theta. Secant theta, 1 over cosine theta. Cosecant theta, 1 over sine theta. They are not only definitions, they are also identities because, somebody? Anybody? Okay, but why did I say that it's an identity? Because it's always true for every value of theta. It is not, what's the other kind of equation? It's not a conditional equation. There's a table here on page 219 that shows you some of the different identities. Even odd identities, sine of negative theta equals negative sine theta. Cosine negative theta equals cosine theta. These are, they're all familiar to you. We've worked them out. We've looked at them. We've shown how and why they're true. We've proven that they're true. The only new information I'm giving you about these now is that they are not just true, they are identities because they're always true for every value of theta. That will not always be the case. Sometimes, as you will find out, as you've already found out if you've started working the homework from this chapter, sometimes those identities that you're asked to show, to prove, aren't at all obvious or clear cut. So they give you a list of 4 algebraic techniques that will help you to simplify these trigonometric expressions. And the first is the one I just shared with you. Rewrite everything in terms of sine and cosine. That's generally going to be a very good place to start. They're also going to it's always good to generally, not necessarily always, but it's generally a good place to start with the more complicated side of the equation. Try to simplify the complex rather than trying to complicate the simple. All right? Why would that be a good idea? If you're working towards simple, then you're working towards a more constrained result. Okay? But if you are trying to go from the simple to the complex, well, there's always, you can always make a whole wide variety of choices at every step that greatly increase the complexity, but will not necessarily bring you to where you're headed. It's like trying to, if you've got a tree and you start off in one branch and you're looking to find your way to the roots, that's a whole lot easier than trying to follow from the roots, trying to find one particular point on one branch. Okay? Every time you make a choice, you can be led in a further and further away from the result that you're looking for. But if you start at the complex and work your way back to the simple, it's generally going to, your choices are generally going to funnel you towards your goal. Rewrite sums or differences of quotients as a single quotient. This table is on page 223 if you want to look it up. And of course they say always keep the goal in mind. You've seen me go through this right up here trying to work problems in homework. You can start doing a solution, but if you don't keep your goal in mind, where are you looking to go? basically just another way of saying what I was already saying a minute ago. Start at the complex and work your way to the simple. That way it's easier to keep your eye on the goal, where you're headed, what you're looking for. Let's, we already did this one. There's another simple one, and it's a variation of the Pythagorean identity. Establish this identity. Let me get a place to write. Well, that one's just trivial. Let's see if we can find one that's. Here we go. Let's look at simplifying cotangent theta divided by cosecant theta. Just try to simplify this. How would we simplify it? Let's rewrite it in terms of sine and cosine. Cotangent of theta is cosine of theta divided by sine of theta multiplied by 1 over the cosecant of theta. Well, what's cosecant of theta? It's 1 over the sine of theta, so that means we're multiplying by sine theta over 1, which is dividing by 1 over sine. They cancel, and the whole thing reduces to just cosine of theta. Does everyone understand what I meant when I did this right here? Instead of division is just multiplication by a reciprocal. So if you're dividing by 1 over something, that's just the same as multiplying by that thing. Dividing by 1 over x is multiplying by x. Here's a good one. May not be quite so simple. Show that cosine theta divided by 1 plus sine theta is equal to 1 minus sine theta divided by cosine theta. How would we begin to establish that? Well, that's a good place to start. If we multiply both sides by cosine theta, we end up with cosine squared theta over 1 plus sine theta is equal to 1 minus sine theta. And now if we multiply both sides by 1 plus sine theta, we end up with we get cosine squared theta is equal to 1 minus sine theta times 1 plus sine theta. And what does that equal to? That's equal to 1 squared minus sine squared theta. What do we add? We add sine squared theta to both sides, and we get cosine squared theta plus sine squared theta equals 1. And like I've said, that is the identity that you will run home to every time, or very nearly every time. Once you can show this identity, you've established the identity. And we got a couple more minutes. Let's look at one more that's maybe a little more complex. Kind of give you all a good start on getting on the homework. Sine theta over 1 plus cosine theta plus 1 plus cosine theta divided by sine theta is equal to 2 times cosecant theta. All right? How would we start this? Well, let's start by rewriting this as 2 times 1 over sine theta. Well, it's just 2 times sine theta. Or 2 times 1 over sine theta. All right. Multiply through by sine theta and we get sine squared theta plus 1 plus cosine theta. That's over 1 plus cosine theta is equal to 2 times 2 over sine theta. No, it's equal to 2. Multiplied through by 1 plus cosine theta, and we get sine squared theta plus 1 plus cosine theta squared is equal to 2 times 1 plus cosine theta. What's 1 plus cosine theta squared? So, that'd be 1 plus 2 cosine theta plus 2. Did I do that right? No, plus cosine squared theta. Did I do that right? Yeah. When we square 1 plus cosine theta, we end up with 1 times 1 is 1, plus 2 times cosine theta, plus cosine squared theta, equals 2 times 1 plus cosine theta. We running out of time? We sure are. Yeah, no, it's time to, everybody's got to get to their class. It's on page 222 if you want to see the rest of it. Thought I could get that one out in time, but guess not.